ADCs by Professor Jose Martinez, Silva Martinez from Texas A&M. So today in this talk, we are very honored to have Professor Carlos Saavedra. He's a professor and currently head of the Department of Electrical and Computer Engineering at Queen's University in Kingston, Canada. He is a co-PI, principal investigator on the platform for advanced design leading to manufacturing in microwave and micro and nanotechnology. He's headed the RF lab in the Queen's University for many, many years. This current project is a multi-million-dollar Canada project funded by the Canada Foundation for Innovation. He's a former chair of the Natural Science and Engineering Research Council, NSERC, in Canada. He participated in several projects and grant review panels at the National Science Foundation in the US. He was a external reviewer for the Netherlands Organization for Research. He's currently the guest editor of the IEEE Open Journal on Antennas and Propagation, section on liquid antennas, topic that he'll be speaking about today. And he was previously associate editor of the IEEE Transactions on Microwave Theory and Techniques. He's very active in this field of microwave for many, many decades. So it's really an honor to have such a distinguished speaker here with us today. And I welcome all of you then to post questions here in the channel as he talks along about this very exciting topic. Thank you again very much on behalf of the IEEE South Brazil section and chapters, Professor Saavedra. The floor is yours for your presentation. Thank you very much.
Thank you very much, Professor Bumpy, for your kind introduction. And I am very pleased and honored to have been invited to present here to the IEEE Solid State Circuits and Electron Devices Society Joint Chapter for South Brazil. Good afternoon, everyone. So the topic of this presentation is going to cover RF circuit design and antenna design using fluidics. This is a new area that has emerged in the last 5 to 10 years, specifically in the RF area. And I want to keep the conversation or at a conceptual level, for lots of technical details. Of course, I have the references, the papers that we've published in my group and others groups. So I want to keep the conversation here today at a conceptual level, primarily. So I will give you here the outline of the presentation. First, a general overview of fluidics, microfluidics. Talk about some specific topics that we've looked at in active circuit design, for example, a low phase noise oscillator tuning using fluids as a demonstrator case of what you can do with fluidics and RF. And then I will talk about circuit modeling of fluidic components with the eye to allow us to do more complex circuit design with fluids. As circuit designers, we want equivalent circuit models to be able to build up. So I'll present a circuit model for this. That is very versatile. And then I'll talk about microwave filter tuning of microwave filters, and then I'll move on to antennas and then conclude. So first, I'd like to introduce you to my research group, to a number of the researchers in my lab, student researchers and postdocs who have been working with me on this topic. And so at the present, I have postdoctoral fellow Miguel Rufui and 4 PhD students, a visiting PhD, and a master student, Hayden Banting, who's completing his master's and will be moving on to PhD in January. A brief overview of the infrastructure that we currently have in the RF lab at Queens. So, we have vector network analyzers to 40 gigahertz and 65 gigahertz, spectrum analyzers and signal generation Recently, we moved up to 110 gigahertz. We have this capability now. We also recently, meaning in the last 3 years, built up an antenna and a echoic chamber to do the work that I'm going to show here today. And we have IC probing, and we have some infrastructure to allow us to build, make PCBs in-house for this work on fluidic electronics. And now just a brief, very brief overview of the Department of Electrical and Computer Engineering at Queens. We have at present 30 full-time faculty members, 6 cross-appointed faculty from other departments like computer science and mathematics. We have recently faculty hires. We've expanded in the area of in the devices area, and, the physical electronics. So we had a recent hire in nanophotonics and another hire in sensors and 2D materials. Overall, we have 180 graduate students. About roughly half of them are PhD. The other ones are masters or Master of Engineering. And we have over 750 undergraduate students. So here is an image of the Queens campus and our building, the Walter Light Hall, which is where my department is over here, circled there in yellow. So we're right next to Lake Ontario in the Great Lakes. Okay, so now some general remarks about flexible electronics. So this area, of course, is well known to us. It's very much of interest in, for example, for wearable devices. It's very much of interest for conformal, putting it on conformal surfaces. And of course, here I have some representative images of circuit boards that are flexible, and the top two are clearly flexible. This one is the one bottom left is of course stretchable, and here in the bottom right is a phone that you will probably have seen, of course, in recent times. It's a product by Samsung. It's a foldable phone, and of course, what all these have in common is that in a number of cases, you have polymer substrate, and then you can have, for example, the transmission lines, the traces can be ink printed, or it could be evaporated metal in other situations, depending on how much flexibility you're going to demand of the flexible electronics. So this area, of course, has a very strong industrial interest, and there are, of course, a number of products out there. What we're interested in is thinking a bit more about signal propagation in these substrates, and what the RF community realized after quite a while that microfluidics had started is that fluids actually also have properties that are useful for electronics. So let me just say a few words about classic microfluidics. This subject area really had its origin around the same times that MEMS started. Work in this area began at a big scale in the 1990s, early 1990s. That was the really the takeoff point of MEMS and also microfluidics. And of course, these two areas had the intellectual origin of the Richard Feynman, a very powerful case for studying things at this scale, and so this actually started to happen in the 1990s, and now microfluidics since the 90s until again about late 2000s and early 2010s was almost exclusively the domain of people working in the chemical engineering, chemistry, of course, to study reactions at a micro scale. And of course, there were people in the area of electrical engineering, working in microfluidic, but with applications in the bio area. Now, where we started to take a look at this for RF was with this realization that, you know, let's look at these properties, right? Fluids come basically in two types that are useful for us. They can be useful. One is conductive fluids. This is the case, for example, of compound like Eutectic gallium, which is a liquid at room temperature. We all know about mercury being a liquid, but for obvious reasons, that's not a compound that really we are much interested in looking at for general work here in this area, although some have, but not so much anymore. And then, so what you can do with these conductive fluids is you can use them for example, on-off switching, right? You know, you close a gap with a liquid metal, open the gap, and then, you know, you have an on-off case. Then the other thing that you can do, and this is where it starts to become particularly useful for electromagnetic structures, is that you can make a transmission line of a liquid metal, and you can extend the length of that transmission line, and then you can then have frequency tuning, because if you have a resonator, you know, that is a transmission of a certain length, of course, then the resonant frequency will change immediately. And in the area of antennas specifically, tuning of antennas has always been a particularly challenging topic. Why? Well, first of all, if you think about an antenna, you know, it radiates at a frequency that is determined by the geometry, the physical geometry of the structure. So your choices are somewhat limited for tuning it. You can either add metal or remove metal from the antenna, which again, very difficult to do under normal circumstances. The one case that you will be familiar with, where you actually extending the length of the metal antenna is, you know, with, you know, let's say an old radio antenna where a dipole where you actually extend it, you know, out of the radio and put it back in again. That is an example of you actually changing the length of the antenna, right? There have been work on tuning antennas with semiconductor devices, but again, there are some limitations there, particularly with respect to, you know, power handling of the semiconductor device. And if you keep in mind that antennas are, of course, at the front end of a wireless system, and for, say, transmission, you're usually transmitting a good amount of power, so linearity is actually very important. And again, semiconductor devices bring that limitation with them. The other type of fluids that are used in microfluidic electronics are dielectric fluids. And here, for example, you have the case of water. It has a dielectric constant of 81, a very high dielectric constant. Of course, it's a lossy compound, but I'll get to that in a moment. So if you have a transmission line and you put a droplet of water, you don't need too much water on top of the transmission line to change the phase velocity of the wave propagating the transmission line. So the moment you change the phase velocity, then you have a tuning effect, right? That you can then use for, you know, tuning of filters and tuning of a number of other things, as we'll see. You know, there are other compounds that are not as lossy as water. You know, oils are not very lossy. Then you have alcohols, and there's a plethora of compounds actually that you can use. The question is, what is their permittivity? And so we've actually done a study, a comprehensive study of many of these fluids, and we've characterized their permittivity response over frequency out to 40 gigahertz. And that paper was recently published in the MTT Transactions, and we've put a numerical model to the data so that anyone can now basically use that data for their own simulations and designs. Okay, so why fluids? Well, you know, they have a longer lifespan compared to mechanical tuners, right? Longer lifespan than a micromechanical device. They're also low distortion because they're not semiconductor. They have low distortion, and they also are low noise. And I'll show some results to that effect in a moment, a representative example. Now, what are some of the issues with fluidic design? So let's just get right to it. One big issue is the operating temperature, right? So if you're using water, we know what temperature water freezes, so then you've got a problem. However, you can mitigate this problem. You can begin to mitigate it anyway by mixing it with other compounds have a much lower freezing point. So for example, here in this table, I'm showing what happens when you mix water and ethanol. And so when you have, say, a 70% mix water to ethanol, the melting point drops to -15. And then when you have 90% ethanol, you're down at -73, and so on. So depending on your application, you can, in principle, find a dielectric fluid to meet your specification, at least in the low temperature side. What you also have to take into account, of course, is that your permittivity will change, right? Over depending on what that mix is. But then again, you can characterize that. The other thing with fluids, of course, is the response time. If you have fluids moving in a channel, clearly your response time is not going to be comparable. Your switching time, for example, of an on-off switch will not be comparable to electronics. So if speed is important, then you will want to stay with electronics. So what situations do I not care so much about speed? Well, there are actually many. I can give you a very simple example. If you're trying to, let's say you have an antenna that is, you're steering an antenna fluidically to track a person walking down the street. Well, the speed of a person clearly is slow enough that you can track, or even an automobile or some other moving object. So it really depends on, of course, as always, what is the application that you have in mind. Okay, so here's some previous work by others on fluidic antennas. And here at the top, there's a dipole antenna on a polymer substrate, and you can bend it. Of course, when you bend that, the radiation pattern is going to change, right? But here it's just demonstrate what you can do. But if you have such an antenna on a polymer, you can conform it to the body, for example, in a wearable device. Here at the bottom, we have another image of a different type of antenna. It's called a patch antenna on a polymer, again, stretchable. And here are some prior works showing tuning of filters. And here, for example, at the top is a tunable filter with a dielectric fluid. And these filters are the one at the top and the bottom. They basically one resonator or two resonators max. And so you can see the tuning over multiple gigahertz here. Okay. So let me move on to some work now that we've done at Queens. And we did, for example, work on an oscillator, a tunable oscillator, a low noise. And this was done using distributed elements. And so we had a package transistor. And this is the, say, classic microwave way of designing, for example, an oscillator. So you look at the transistor as a two-port. You have on the right-hand side here of the image, you have, for example, a resonant transistor, and also providing bias to the transistor. So you look at that as a network, and then on the left-hand side you have the load, which is Z0, and then you have a matching network between that load and the transistor. So in the microwave view of things, one way to do this design is that you want to ensure that the product of the reflection coefficients gamma out and gamma t is equal to 1, so that you have in steady state, that's what you will have, right? And then the same thing over here on the left-hand side, the product of reflection coefficients gamma L and gamma N will equal 1. So I'm not going to get into how this works because this is pretty standard microwave oscillator design. But what I want to point out here is that how can we do fluidic tuning of this? Well, as I mentioned before, if you have a droplet of, say, water with an epsilon R of 81, and your substrate has a lower epsilon R, dielectric constant, relative dielectric constant of, say, 3, 4, 5. If you just put a droplet on top of a transmission line, you will change the wave propagation velocity enough. So that'll tune the transmission line. And when you tune that transmission line, what happens is that the frequency at which this condition is satisfied will change. So then you change the tuning frequency of the oscillator, right? And so you can put droplets on the matching network on the output, and then you change basically the frequency at which this other condition is satisfied. And so we did some experiments with that, and so here's the actual oscillator circuit. The device was a package p-hemped. There's a part number from Broadcom, and so the source is grounded, DC grounded, and we have a length of transmission line connected to the source, and this actually helps to make the network unstable. The resonator structure is here in the dotted yellow line. It's a substrate integrated waveguide resonator, and I'll talk a little bit more about that in a moment. And then we have the matching networks, right, between the transistor, the drain transistor, and the resonator. We have the feed, DC voltage feed, and so on. So let's talk briefly about the resonator, and I am actually missing some images here, so I want to skip over that. I'm going to go right to this page here. So this is the resonator. Okay, a substrate integrated waveguide is it's a type of transmission line used in printed circuit boards that has some similarities with rectangular waveguides used in microwave engineering. Now, rectangular waveguide is a hollow pipe, and it can have different cross sections. And rectangular is the most common. You can also have circular, and these waveguides have a cutoff frequency, a lower cutoff frequency. Below that cutoff frequency, you don't have any propagation. So they start propagating above a certain frequency. Now, with these substrate integrated waveguides, what you're trying to do is replicate, in a way, the waveguide, the rectangular waveguide on a printed circuit board. And the way you do that is that you put via holes between the top layer of the board and the bottom layer, and you plate it through vias. And if the vias are spaced closely enough, then as you know from basic electromagnetics, then this will actually look like it's a solid wall to the wave, right, propagating the structure. So we use SIWs because they actually have minimal radiation loss compared to other transmission lines like microstrip or coplanar waveguides. So here in this image is a SIW resonator. Here is the port, input-output port. Of course, there's only one port in this resonator. And so this resonates at this particular resonator was designed for 5.12 gigahertz, and this shows a full wave electromagnetic simulation of the response of the resonator. And so that's the resonator that we used on the circuit. And this is the layout of the circuit. And here is an image, a photograph of the circuit board. And so you can see that the transistors here, the resonator is over here at the top. I think I'm going to change colors here of marker. Okay, so here is the resonator, And here are the water droplets. You can, make them out here. When we look at the, okay, this is the test setup, and in the interest of time, the only thing I want to point out is that we have a 20 dB attenuator between the oscillator and the spectrum analyzer to protect the spectrum analyzer. So in this measurement, so this is the oscillation output, free running spectrum. So it's basically minus 20 dBm at the spectrum analyzer. So it means that's 0 dBm output power. And when we add the water droplets, we're able to tune the frequency of this oscillator over about 150 megahertz. So it starts off over here at 5.05 and then it ends at 4.95. So you notice that the lowest frequency here is 5.05, whereas the resonator had a resonant frequency of 5.12. That is simply because that was just, the 5.12 was just the resonant frequency of the oscillator alone. Here, this is of course the whole oscillator structure with other transmission lines and things like that. This is not a complete circuit, so the drop is not unexpected, the change in frequency. So 150 megahertz tuning range by adding water droplets to the oscillator circuit board. And then here is the measured phase noise without water droplets at the free running frequency, 5.09 gigahertz. The phase noise of the circuit is minus 125 dBc per hertz at 1 megahertz offset. And after we tune it to 4.94, the phase noise is minus 124. So it's a negligible deterioration. It's almost less than a 1 dB hit on the phase noise. So this helps to show us that with the fluid, we don't see a change here in the phase noise, which is actually a good feature. Okay. Let me so earlier here, and when I showed you this image of here, the water droplets they were usually located, and we had, we knew how to position them, but of course it would be much better if we have a way to model what the droplets or what the fluid is doing in the circuit. Because once we have that model, of course, then we can go to the simulator and do much more. So that got us working on developing a circuit model for a fluidic channel. So what we looked at is, instead of a droplet on top of the transmission line, we looked at having a transmission line with a channel dug underneath it, and then filled that with water here. And then if we put this pi model to it, to that circuit, we can immediately derive an ABCD matrix, right? It's a lumped element model. So we can derive an ABCD matrix for it. And once we have an ABCD matrix, then we can solve, of course, for the impedances in the pi model, which are given here on the top by these two expressions. Now, to go from the model to actual values, right? Real and complex values of the impedance there. We need a way to measure that or get that information. So, we don't directly measure ABCD parameters with an instrument. What we can measure, for example, are scattering parameters, which is the main network parameters that we use in a high frequency. So you measure the scattering parameters of that structure, right? And then you can just convert from ABCD to S parameter and vice versa, and then you can get the actual expressions. Here's in this page of an actual channel, and channel of given dimensions here is shown. This particular channel has a length of 1 millimeter. It's filled with fluid. The height of the substrate is 1.52 millimeter. Well, take that back. The length of the channel is 0.5 millimeter. The length of the transmission line is 1 millimeter, and so on. So when you go through this process, right, of finding the ABCD matrix, getting the S parameters, and then getting the values. This is some example values that you get, all right? Okay, so we have a model. What can we do with it? What's next? So what we did then was, let's use this model for something of actual engineering use. And one very commonly found component in RF systems is the 90-degree branch-line coupler. It's a power splitter. So here's change color here again. Say you have an incident signal at port 1, and then over here at port 2, you have port 2 and 3, you have an equal power split. And port 4 is isolated as long as all the ports are terminated in 50 ohms. And then there's a phase shift between ports 2 and 3 at 90 degrees. That's hence the name 90-degree branch-line coupler. So we have here in this coupler 4 segments, 4 transmission lines here that I'm circling. These two have the same impedance, the same width, have a different width, the vertex. So what we looked at is, okay, if we dig channels underneath each one of these transmission lines and we fill them selectively with water, we should be able to tune the center frequency of the structure. Now, in the standard branch line coupler, each length of each arm here, each one of these arms I've circled has a dimension of a quarter wavelength. So this is actually tuned at a center frequency that is a quarter wavelength given by the length of these transmission lines. So in order to tune the center frequency of this power coupler, what we want to do is fill these channels underneath with water or some other fluid. And in fact, in this case, we use ethyl acetate because it's less lossy. And let's see what we get. So the first thing actually that we went about doing was to actually extract the equivalent circuit model for each one of those channels. And so there's only 2 types of channels, right? There is a channel that's on the top lines, and this is actually a wider transmission line than this. So we needed 2 different models for those channels. So we got those, and they're listed here. And then we model what happens when the channel is filled with air and what happens when the channel is filled with ethyl acetate. And so we have a different set of lumped element equivalents for that. So then we went into our simulator, ADS, which is what we use here for this. And we simulated the response to this. And then we did full wave electromagnetic simulation to verify. And then we followed that up with an experiment. So let me just show you here the results. So when the power coupler is completely just devoid of any fluid, it's just air channels everywhere. The center frequency is 2.2 gigahertz. And then when we start filling with ethyl acetate, you can have several different combinations, of course, but just for this presentation here right now, I'm just showing you the 2 extreme cases, whether it's completely air filled or it's completely filled with ethyl acetate. So when it's completely filled with ethyl acetate, the center frequency drops to 1.8 gigahertz. In this case, then we have a good tuning range, and actually have a photograph of what the backside looks like with the channels underneath. Now you see that there's no ground plane here. Well, what happened here for this prototype, what we did is that once we filled it with the fluid, we restored the ground plane. We used copper tape to restore the ground plane to be able to do the measurement. And so the table here at the bottom shows basically the tuning range and then the percent error as compared to between the measured and the modeled with the equivalent circuit model. Okay. And so the error difference between the modeled and the measured case is below 3%. So we were happy about that. And this work appeared last year in Microwave Letters. Okay, so now I want to move to filter some filter designs that we've done, and these are microwave filters. So just a very brief overview of how we design microwave filters. So these are transmission line based or waveguide based filters, and if you're going to design, for example, a filter with a Chebyshev response, it's actually very much the same as when you are designing an RF analog filter using lumped elements up to a certain point. So, you go through the same process that, you have your response, you find the filter coefficients, in the well-known tables for these. I'm talking very specifically about, and there where things, of course, diverge is when you do the actual filter synthesis, right? When you're doing lumped elements, you just need to find the actual value of design. The extra step, and it's a challenging step, is of course you have to then convert that equivalent circuit model into a physical structure consisting of physical resonators, waveguide type resonators that will give you the filter response, right? So that's actually the extra fun step that we take, so to speak. So here is a SIW resonator, and this is just like before, but here I'm not showing any inputs or outputs. It's just a resonator, and so this will have a very specific resonant frequency given by the dimensions of the structure. Now you'll notice here that this is square, so when you have a resonator, then you can actually have degenerate modes, and you can do a whole lot more things when you work with degenerate modes in this structure. So I'm not going to really get into that here in this presentation, but just to let you know that when you have a resonator that is actually is square, a whole lot more design opportunities open up, and we have taken advantage of that in some other work. But I'm going to keep it here to just the case of where this is resonating and stay at one frequency in the interest of time. So how do we tune this using fluids? So what you can do is you can put some pockets, carve out some pockets in the resonator. So here I now have two resonators, and now they're actually connected together, and I'll talk about that in a minute. But carve out some pockets, and you deposit some fluid of a certain dielectric constant that is different, of course, than the dielectric constant of the resonator, of the SIW resonator. And so then you're just changing, you're changing the field distribution inside the resonator, and then that gives you a change in resonant frequency. So here, to make a filter, you can of course make a very simple filter with one resonator, and if you fill the pockets with water or ethyl acetate or some other compound and remove it, then you can have tuning in the frequency. Of course, to make more interesting resonator filters, sharper filters, you need multiple resonators. So here I'm showing two resonators, and so there's an opening in the wall here where it says position W. There's an opening in the wall between the two resonators to, of course, allow for energy coupling between the two cavities. And you can make these resonate at different frequencies, in which case, of course, you're going to have change the bandwidth of the filter, and this more resonators, sharper skirts, wider bandwidth if you want. Okay, so here is this is just for illustration purposes how you would couple energy in and out. So here at the outside you have, for example, a microstrip type transmission line, and goes into the resonator, and then you have the electromagnetic coupling, and then here's on the outside. So here are some experimental results on a 3-resonator Chebyshev filter that we designed. And so you fill the pockets, or you empty the pockets, and you can have this type of tuning here of the center frequency of the filter. So in the case of where the red traces are when the pockets are empty, so it's a higher frequency, so standard frequency about 3, and then when you fill them with the fluid, then you drop that to a lower frequency, and it's about 2.8 gigahertz center frequency. So we a variation of this work, actually a next version of this work that we did is going to appear at a European Microwave Conference later in early January 2021. Okay, so it turns out that you can also tune these resonators, these SIW resonators, or actually many other resonators, not just by changing the dielectric permittivity, inside the cavity. You can actually also introduce short circuits at different locations, and basically, well, you force the electric field, to, of course, go to 0 where that short is, and that'll change the volume of the cavity, and that'll tune the frequency, right? Because in these electromagnetic resonators, right, in these structures, of course, the resonant frequency depends on the physical size of the cavity. It depends on the physical size and on the dielectric constant of the material inside it. So in the previous slides, I was showing you what you can do, for example, when you change the dielectric constant inside the cavity. Now we're going to actually change the volume of the cavity, okay? And you change the volume or the geometry by, you can introduce posts to short out top and bottom. So here is this is a 4-resonator filter that we designed, and you can see here are some holes, and these actually you can fill with liquid metal. And so when you fill them, you reduce basically the volume of the cavity, and you can tune the frequency. So I don't have too much time actually to go into how this particular filter works, but it is actually quite different than the filters that the previous filter I just had. I mean, this filter has 2 transmission paths. Okay, you have a direct transmission path from input to output, and then you can actually have signal transmission from this here to here. So it's a coupled resonator filter, right? And this opens up other possibilities, and so we have these square resonators as well. So then we're working with tuning of the different modes and so on. But at the end of it all, what I want to show you is the response. So these are measured and simulated results, right? And so at the top we have the S21, so the transmission through the field, quasi-elliptic. As you design these to have transmission throws right very close to the band edges, right, to get that really sharp. And we by putting in fluid and removing it in the different pockets, we were able to tune the frequency of that filter over almost half a gigahertz actually. So to our knowledge, this is the first quasi-elliptic filter with fluidic tuning that's out in the literature, or this is actually this has been submitted. So when it comes out at some point, so that to our knowledge is the first one with showing this kind of tuning, quasi-elliptic response. And so I have one more filter structure that I want to mention here. That so this is actually an early filter work that we did, and this was this particular project was a collaboration with another university. And so what this one is a differential filter, and so you have you have 6 resonators. So of course you can see that basically right down the middle you have a symmetry plane, And so these differential filters are of interest for doing common mode rejection and things like that, right? And circuits and so on. So we have 3 resonators on the top. The loop set that. And now we have here transmission lines that essentially will help us tune the frequency of the filter. So let me go to the next slide, which is actually looks at this in a little bit more detail. So this is just one pair of resonators, right? So top and bottom. And if you add a droplet, I'm going to change the color here of my something a little bit more distinctive, perhaps. If you put a droplet of liquid metal here, then you essentially create a physical short there. I mean, there is a virtual ground there anyway, because it's a metric structure, so you will have a virtual ground. But here, if you put a liquid metal drop here, you actually, of course, create that short there. And so that'll tune the frequency of this ring. When you remove that, liquid metal dot, so you switch it off, then what ends up happening is that you have the transmission line attached to the upper ring is a bit longer, right? And it goes here as well. And the same for the bottom one. So you're basically changing the length of this transmission line attached to the resonator. And in the paper where this appeared, there's detailed equations showing how that tuning behavior works and some closed form expressions to allow you to predict what is the tuning frequency of the filter. But so now I just want to jump to actually here's the image of the filter, and that's the citations of the paper. But here is actually the type of tuning that you can do. So in state 1, when there's no, when you have the liquid metal droplet there, this filter has a center frequency of 2 gigahertz. And when you remove the droplet, you're in state 2. So then you drop the frequency of the center frequency of the filter to about 1.5 gigahertz. The bottom is the common mode rejection of this differential filter. And, so basically you're seeing about 40 dB, right? Okay. All right. Now I'm going to spend the last 10 minutes or so talking about antennas, some antennas that we've designed. So first, some general background. This is, here on the left, top left, we have the half-wave dipole. All right. So the dipole antenna is really the most fundamental of antennas, and it is very, very much a very good case to start from which to start building things, right? So here on the top right, we have the radiation pattern. Well, this is let me take that back. This is a snapshot in time of the electric field generated by, say, a half-wave dipole, okay? And it's just the electric field, and so this is the E theta component, okay? Now, the electric field, and then for the magnetic field, H sub phi here, and the far field are shown here on the bottom left, okay? So, when you do a 3D, radiation pattern plot, here's shown on the bottom right of what the dipole, the radiation pattern in 3 dimensions of a dipole antenna looks like. And essentially, right, it's a donut-shaped structure, right? So it's omnidirectional. Another reason why, the dipole antenna is very much of interest, engineering interest. It's omnidirectional. It has low gain. You have nulls here at theta equals 0 degrees and 90 degrees, and that's all contained in these two expressions. But what I want to say here is that, okay, so if you want to tune the frequency of this dipole antenna, you have some choices, right? Well, the main choice is you just have to make this dimension of the dipole physically larger, right? You have to extend this somehow. This is how it generally works. Now, before I go there, another antenna that is very much closely related to this, because it derives from this, is the monopole. So for a monopole antenna, and I know that there are antenna experts in the audience, so of course this is for the general memory refresher for everyone else. So for the experts, please allow me to just do this very simple review. So one thing that you can notice here about this, the diagram on the top right, the snapshot in time of the electric field of the dipole antenna, it's symmetric, right? There's a symmetry plane right here, right? There's a nice symmetry plane, right? There's a nice symmetry plane right there. And of course, if you do the same thing here, right? We have basically a symmetry plane here. From a kind of an abstract point of view, we have like a virtual ground right there, right down the middle, right? Because this is differentially fed. This isn't, these two halves of the antenna are differentially fed. So if you actually put a metal plane, a ground plane all the way down the middle, what you end up with is what we know as the monopole, right? A monopole. And the monopole is, of course, is again a fundamental antenna structure. And in the cars, for example, not so much these days, but up until 20 years ago, many cars and still had the antenna that would come out of the back, right? And you could the retractable antennas and so on, right? I mean, that's essentially a monopole where your car is the ground plane. Okay, so by thinking about the monopole, then we just have to tune one length, right? So we just have to think about how do we tune the one length, and if we put a ground plane there, then we get this tunable antenna. We tune the frequency of the antenna. So here's what we did about this. So this is a work that we did, and this appeared last year in Antennas and Wireless Letters, Propagation Letters. So we have a monopole that we implemented on a circuit board. Okay, so this is the top plane, and then in the bottom plane is the ground. Okay, so that's the ground plane. And then what we did was that we put we dug out some channels underneath the monopole. And I'm going to change the color here. Okay, so we dug out some channels underneath the monopole, and we filled them with fluid. And by doing that, then we actually, because the water has a high dielectric constant, then again you're changing what the wave sees, right, in this transmission line. You change the wave velocity, and so the length of that monopole now looks like it's a different length when you put water in or when you remove water, and so then we can tune the frequency. So that was the premise of this work. And so let me get rid of that. So let's just get down to, let me just show you some results. So these are measured results. So this is a measurement of the reflection coefficient of the antenna, okay? So an antenna, when it's radiating, so you send a signal into an antenna, right? And at the frequency at which it radiates, you want all the energy. The energy is leaving the antenna, right, going to free space. So you expect to see a low reflection coefficient when you look at that port at the radiation frequency. So this here shows how the reflection coefficient changes as we change the fluid into the antenna. So we're tuning it here from 4.5 gigahertz to about 5.75 gigahertz. Okay, so by just making these channels underneath the monopole and filling them with fluid, we can change the frequency of this antenna by, about 1.5 gigahertz. And here are some radiation patterns measured and simulated. And so this is the electric field, right? E plane. And now here you see that the, the pattern looks like this. And here's this. So this is just the way that my student plotted this, right? I mean, so here's theta equal to 0 degrees. So, I mean, this is kind of sideways, right? Because the way he put the antenna, anyway, in the measurement chamber, it just this is again just a rotation of the graphs. But so, and then here is the H plane. So it is pretty much omnidirectional, right? I mean, there are some differences a bit between the measured and the simulated, but you see that the H plane, the magnetic field here really is pretty uniform around the full sweep, so it is omnidirectional. And now I know that so here we have a comparison table of our antenna with other fluidically tuned antennas that have appeared in recent times. So we are reporting the highest the highest efficiency, antenna efficiency, but this is gotten through. I mean, we did measure results, but the efficiency was simulated. But actually here, the impedance bandwidth of the antenna, ours has the widest one at close to 30%, and this is measured. And okay, all right. So the last thing I want to mention here today to show you is some very recent work that is about to appear in Transactions, Antennas, and Propagation. And this is an antenna with a lens incorporated into antenna, and the lens actually is you can tune the lens, right? You can do beam steering with this antenna by depositing fluid into the lens or removing it. Okay, so this, to our knowledge, is the first ever report of a fluidically tuned microwave millimeter wave lens, and it's integrated here into this antenna. So first, I'll actually just say some general words about this particular antenna design. So this is quite different from what I just showed you. This one is called the Vivaldi antenna, and Antipodal Vivaldi antenna. So you have on the top metal here shown in red, and that's connected here to the center pin of the connector. The bottom side of the substrate, so I've made the substrate a bit transparent so you can see the bottom plane. You have the ground plane, okay? So, this taper here is exponential, which is what gives it the broadband response, right? I mean, this particular antenna has like a 4 gigahertz bandwidth, but I mean, we've made and others have made antennas, Vivaldi antennas, just basic Vivaldi antennas with, 10, 20 gigahertz of bandwidth, right? It's the exponential taper. So when this radiates, right? Oh, that doesn't show too well. Just use a different color. Oops. Anyway, so when this radiates, field is doing. So it radiates out, on the edge of the board, okay? So it radiates. This is the electric field. It radiates on the side. The neat thing actually about these full waves EM solvers today is that you can actually also import into this full wave solver. You can import the actual connector, and we found that actually this makes a difference. So if you want to get the best possible correlation between what you simulate and what you measure, you actually also need to import the CAD model of the connector, because everything matters, right? You know, especially as you get into higher and higher frequencies and the wavelength gets shorter and shorter. You know, like at 30 gigahertz, you know, the free space wavelength is 10 millimeter. And, you know, that's getting pretty close to the size of the actual connector here, right? So anyway, so that's the Antipodal Vivaldi element. That's the basic thing. So what we did was we took that element, this is the top view now, and we put a protrusion here of the dielectrics. So, I mean, Vivaldi antennas with lenses, you know, they have been studied in the literature before, right? What hasn't been done is to actually change the characteristics of the lens using fluids. So we put, you know, we protruded the substrate, created a lens type geometry, right? And then we put pockets, built pockets into the substrate. And as we filled them with fluid, ethyl acetate in this particular example case, you know, we changed the local dielectric constant, and then we can start steering the beam in different directions. Okay, so that's an image there of the actual antenna. So yeah, so this paper actually is already on IEEE Explorer, right, as the early access. Okay, so here's the fill-in patterns that we use, right? So we can steer in, you know, over a certain range of angles. And here is full wave simulation of how the radiation pattern changes, right? As we fill different areas of the lens with fluid. Now let's get to some measurements. So here in the measurements, so we plotted, this is actually radiation pattern measurements. This is instead of polar, we put them in Cartesian, because we found it easier to visualize in this case. So here we measured from 32 to 35 gigahertz. And so you can see that, you know, as you fill it with the different pockets, right? Here is one case where, you know, here's the angle is at minus 20 degrees. And then here in this case, in another case, it's straight on. Then in another case, you know, it's steered and so on. So here's actually clearer, right? Here's one case, and then here's another. Here's another. So we saw about plus or minus 15 degree beam steering, close to, we'll say 30 overall. And so this interests us, number one, because here you can now do beams. Usually when you want to do beam steering with antennas, traditionally you have two choices, right? Choice number one is you have one antenna element and you mechanically rotate it, right? I mean, this is what they do in, you know, at the airport, you know, with those aircraft radar, right? At the top, you know, at the airport, you know, all those radars, you know, they're just, the antennas are moving around, right? You know, and you see this in ships and all that. So that's one way. Another way is that, of course, you have electronic beam steering, in which case you need an array of antennas, you know, and you change the phase shift, of course, and you know how that works. So you can do the beam steering that way. So here we have actually beam steering with a single element, okay, in one direction. So in fact, what this means is that if we wanted to do beam steering in 2 dimensions, you know, we could just stack, you know, put a few of these antennas in, you know, in series, right? And then we could actually potentially do 2D beam steering. You know, I have more work that I could share with you, but that, you know, I know I'm already actually past the hour mark, and I want to leave time for a question and answer. So I'm going to conclude the talk now. Actually, before I go, I just wanted to show you the gain of this antenna. So this antenna has a gain between 6 and about 8.5 dB over the span, 32 to 35 gigahertz. And you know, there are some other measured results there, S11 and so on. Okay, so to wrap up, some of the main messages here today are, you know, if you're working with dielectric fluids, you really only need small amounts of it to affect in wave propagation velocity. And you can then use that to do tuning of especially passive electromagnetic structures, which has been the more difficult thing to do, okay? Fluidic tuning has advantages in terms of, it has negligible impact on noise, as we saw, as an example. And it also actually has minimal impact on power handling, right? And it's not going to introduce distortion in the same manner that, say, semiconductor devices would. You can do circuit modeling, and once you do circuit modeling of different components, you can then take that in so many other ways, right, in circuit design. And the last message I want to leave here today is that specifically for antenna design, this really opens up many doors that really were not available in antennas in the same way that there were for microwave electronics, circuits and so on, because essentially everything in antennas is size dependent, and so having a way to change dimensions with fluids and so on is actually a very innovative and interesting way of doing design. Thank you.
Thank you, Professor Carlos Saavedra, for this very nice and interesting talk. On behalf of the chapter here, thank you very much. I would like to address some questions that came from the audience.
Yes.
The first one came from Dr. Arthur Lima Neto. His question is, are there any limitations to power levels in those structures due to the use of fluids, or the power levels could be at the same level as when the fluids are not present? And I have a related question. I noticed that in some of the filters, they measured 2-3 dBs below on the passing band from the simulation. Maybe it's related to, you can answer the second question also that I addressed to you. I'm Sergio Ben.
Definitely. Yeah, sure. I'll answer those two. Great questions each. So for power handling, in terms of, let's think about distortion, right? So distortion is definitely not impacted, right, in the same way. And what can happen is that when you have lots of watts of power, of course, what's going to happen is that you're going to heat up the fluid, okay? And so that's going to, of course, there's going to be a temperature increase, and then that will, of course, have other impacts. So there have been studies done by others looking at, for how many watts of RF power, how much do you increase, the system temperature, let's say of DI or some other fluid that you're using. So I will say that there is an impact, but by the time the impact is significant, you're actually dealing with many watts of power. So for medium power, low power applications, you don't have such an issue. With respect to the losses, right? So definitely, there was a drop in the, deterioration, the insertion loss of the filters. There's no question, right, that depending on the type of fluid that you use, that you will have a bigger or lower, you can have a worse a deterioration in the insertion loss. So here's where you really want to know beforehand, before you start designing anything, for example, is what is the complex permittivity of the dielectric fluid you're using. So water, for example, has been very carefully studied, and we know that water is actually quite lossy. Even distilled water is, it gets really lossy, as you see. So, for example, where the dielectric loss is actually much less, and it's much less even at high frequency. So that actually, Sergio, it's what motivated my group for us to take a detailed characterization and a study of the dielectric frequency response of a number of fluids, because that really hadn't been done systematically for a lot of the fluids that we're interested here for this type of RF design. So we've published that data now, it's out there. And so in the future, for example, if I were to say design another filter, I would not use that particular compound. Now I know pretty well that certain oils have a much less loss over a wide frequency band. So it depends on what you're going to use there.
Okay, there's another question by Sheriff, Mr. or Miss Sheriff from Canada. The question is, can the water be modulated using the mechanical waves at this gigahertz frequency, and how compact do you expect such circuits using either water or fluids as dielectric? How compact can those circuits get? And that's the question.
Okay, so I think I heard something about modulation. Yeah, so let me just say off the top that I think we wouldn't use fluids, right, to say modulate a signal. I don't think that's something that is something we would really look at, because there's no comparison with electronics, right? But if maybe one wants to think about intermodulation, distortion, all of that, then the only thing to say here is that it's very low, because that's, of course, is already covered in the I was mentioning earlier about linearity, right? That these are very linear response. I mean, the only thing that may happen is some hysteresis effects that can impact intermodulation distortion, but it is actually quite negligible. I forgot what the second part of that question was.
Well, actually, the idea that Mrs. Sheriff had is meant to mechanically change the shape of the water droplet. So this mechanical modulation, he or she is proposing that would be in terms of mechanically shaping the droplets. Maybe there will be a more sophisticated structure than the fixed walls that you're using, maybe.
Oh yes. So in that regard, it's a very interesting question, which we haven't really explored. And I mean, I think the reason is that what we want is actually a good level of predictability and control. So if you want to change the shape, you actually have to know quite a bit about the surface dynamics, right? The tension and how the molecule or the droplets, that whole, how that surface changes. So we haven't studied it, and there's definitely a subject that I know that people, for example, who do chemistry and chemical engineering, they've thought about it a whole lot more. I haven't considered it, and I think it would be fairly challenging to do, let's say, engineering work that's reproducible, given where things are today, state of the technology.
Okay, there's another question. I think that would be the last one. There is two other questions. Okay, one is from Professor Sandro Ferreira from Unicinos here in South Brazil. He also thank you for this very nice and interesting presentation. And you mentioned in the beginning, Professor Saavedra, that you use ADS in simulations. The question is, are you also using other simulation tools for the co-simulation with the microfluidics, so tools for the microfluidic simulation?
Yeah, so we use the ANSYS, multi-physics ANSYS, and we use a lot, actually, HFSS, high frequency structure simulator. And HFSS has a advanced water fluid model and some other models. We also have access to COMSOL here. We haven't used it as much, actually, at this stage, because actually it kind of relates to what I was saying earlier, that because we have our fluids and very well-defined channels, and we're constricting the geometries quite a lot, so that we're not studying us in our group so much, let's say, the physics of the fluid flow itself, right? That's an area all of its own. So we've basically been using ANSYS as the answer to the question for electromagnetic simulation, and it does have some fluid models for the dielectric properties that are useful.
Okay, now for the last question that comes from Felipe Kalinski from HT Micron Company here in South Brazil near Porto Alegre. Felipe is asking, are the fluids used static? The fluid's velocity could be another point to explore, maybe with coupling your structures that you are building in your lab with micropumps. So using micropumps to change fluid velocity also, if it could be a way to do it. And how it could change by this velocity, maybe some dielectric constant mechanism. And he also thanks you for this great presentation. It generated very much attention in the community. So that's the last question.
Yeah, thank you for all these questions. Yeah, so actually we thought about that, and I was talking to one of my graduate students, and we were thinking of a problem that happens with, actually, this happens with, out in the ocean, in maritime situations where, of course, because of the bobbing of the waves and so on, there are situations where when you have an object that's really far enough away, any small change over here where you are, can have an impact on, let's say, the received. Well, let me put it differently. The scattered signal, right, from an object, and so we've given it some thought, not too much detail at this point, but I think there may be some opportunities to explore there.
Okay. Well, thanks again, Professor Saavedra. This will close our talk. Your talk and question and answer is already 80 minutes, 1 hour and 20 minutes. I think you're tired. And I'd like to say that, here we'll continue on with this lecture series. On November 9th, we have a next one on, high performance op-amp design for pipeline with ADCs with Professor José Silva Martinez from Texas A&M. There is another platform on October 23, the solid-state circuits promoted a webinar by Dr. Mike Shane from University of Southern California on non-uniform sampling methods for analog to digital converters. So the field is very exciting. You brought a new area here in antennas and filters using microfluidics. We congratulate you with that. And on behalf of the South Brazil Joint Chapter, thank you very much. And leave now for your last words for you, dear Professor Saavedra.
Thank you very much, Professor Bompi, and thank you very much for all the attendees. It's been a real pleasure and a privilege to give this presentation to you today. And my contact information is there if you want to contact me offline. I'm always happy to receive comments and questions. Thank you again for the invitation.
Thank you.